Recall, we had a bunch of definitions last time. So Q is a quadratic form. We'll write it as ABC. Quadratic form, by which we mean Q is equal to ax squared plus bxy plus cy squared. And it has a discriminant. Discriminant. What's the discriminant? Does everybody want to just type it into the chat? Everybody knows what the discriminant is. Come on, other than DeBendro. Does anybody know? Thank you. You guys are all just waiting for DeBendro to write in. Yes, everyone knows. Thank you, Sarah. B squared minus 4ac. All right. And the things we learned last time are that Q is degenerate. Degenerate. It's not really a quadratic form in two variables. It's just a quadratic form in one variable. If 4 quack. Yeah, 4ac. Q is degenerate if this discriminant is Stephanie, you're going to write it in? Thank you, Shang. Thank you. Yes. Degenerate if the discriminant is 0. Okay. Then Q is like x squared and not x squared plus y squared. So that's not interesting. Q is, what do we call it? Reducible or something? Reducible if the discriminant is a perfect square. A perfect square. Where? Perfect square. Right? So then Q is like, let's see. Yeah, like xy, I guess, is a good way of thinking about this. So again, it's very easy. So this represents only very few numbers. This represents, well, all numbers, because you just set x equal to 1, and then y can be anything. All right, so these are kind of the things that are immediate. Then we talked about being definite or indefinite. Q is definite, and it could be positive or negative definite. We'll talk about that in a second. If the discriminant is Shang. Right, the sign doesn't change. So it's definite either if it only takes positive values or it only takes negative values. How can we tell that that's the case? What's an easy way to tell whether or not that's the case? You compare it to the quadratic polynomial, which makes a parabola, either a happy parabola or a sad parabola, face-up parabola or a face-down parabola. Is that a parabola, Stephanie? No, that's just a ball. There's a big green ball. Oh, that's a little green ball. Just graph it. Yes, you could graph it. You could graph it, but you can do something much faster than graphing. Because if I give you 1,000x squared minus 300xy plus 76y squared, that's not going to be so fun to graph. Yes, exactly. If D is, so let's see, which one's definite and which one's indefinite. So definite takes only one value. So this definite takes only one sign, either positive numbers or negative numbers, and indefinite if the discriminant is the other way. So which is which? So positive, so think of quadratic forms, think of quadratic polynomials, quadratic polynomials. You have solutions, meaning you cross from positive numbers into negative numbers. So there are solutions, there exist real solutions, if and only if the discriminant is Kevin positive, right? Or 0, but 0 is when it's a double root. 0 is when it's a double root, and we don't want 0. Right. So there are real solutions if the discriminant is positive. That means it has both positive and negative solutions. So that is the indefinite case. Indefinite means it's both positive and negative. If the discriminant is positive, i.e. both positive and negative values. Okay, so definite is when the discriminant is negative. Does that make sense? Definite is when you're either way above or way below the real line. Does that make sense? Is everybody following? All right. So that's kind of the most basic components, the things that you can see kind of immediately about quadratic forms. Let's get to a few more things. So the basic question, again, what do we care about this thing? Basic question is which n are represented by Q. Chang, did you want to ask something? Sarah? It tells me when you guys are typing, but it doesn't tell me what you're typing. What happens to imaginary solutions? Right, so if the discriminant's negative, so there are two imaginary solutions, that means there are no real solutions, so you're always either positive or negative, and that means the form is definite. Yeah, exactly. So that's what. So there are no imaginary solutions. We're looking at roots. So i.e., do there exist x and y integers such that q of xy is equal to n? So the whole story is about whole numbers. It's number theory. We're asking basic questions about whole numbers. Of course, as you already know very well, sometimes we have to go into imaginary numbers and complex numbers and interesting things to answer questions, basic questions. Right, so the imaginary solutions to the quadratic are not there, but they're useful to think about, as we've seen and we'll see more. In fact, we'll see more maybe even today. So the question is, which numbers are represented? All right, so let's look at a few more examples. Let's find. I don't want to just tell you the answer. There's this gorgeous long theory, largely worked out by Gauss. Maybe I should say, much of this comes from his Disquisitiones Arithmeticae. Let's come back to that. Let's play. So give me a quadratic form. Let's try to figure out what values it represents. Somebody toss out some numbers. Something x squared. Everybody write in one coefficient. Give me a value of a. All right, fine. Kevin beat everybody to the punch. 7x squared minus 11x plus 5. All right, first question. Definite or indefinite? Can everyone write in whether this is definite or indefinite? Yukong? Yukong says indefinite, so it's going to take both positive and negative values. Of course, I mean the quadratic form and not the quadratic polynomial. Indefinite, right. And we can see that immediately. So this is indefinite. By the way, can you be degenerate or reducible if you are definite? Sriya? No. Can't be degenerate if you're definite, since the discriminant must be 0. So the discriminant being negative implies not degenerate and not reducible. Okay? You can't be degenerate and you can't be reducible because both of these are forcing the discriminant to be positive. So it's the indefinite ones that you have to worry about. Maybe I'm reducible. Okay. So it is indefinite. There are at least two ways to see this. One is to compute the discriminant. Has everyone computed the discriminant yet? What's the discriminant? B squared 121 minus 4ac. 4 is 20 times 7 is 140. 121 minus 140 is negative 19. Is that what everybody else got too? B squared minus 4ac? Did you guys get negative 19 for the discriminant? Can I get a thumbs up if you're following along and you found negative 19 for the discriminant? Kevin, did I do that right or did I make a mistake? Okay, thumbs up. Okay, everybody's getting negative 19 for the discriminant, as am I. So I got that by doing 121 minus 4 times 5 times 7. Okay, so it's negative discriminant, which means it is definite. It's not indefinite. It's definite. It'll only take values on one side of 0. So is it positive definite or negative definite? Positive definite because, well, just look at the leading coefficient. So it's not only definite, it's positive definite. As we can see from taking Q of 1, 0. Q of 1, 0 in general, so in this case, if I set 1 for x and 0 for y, it kills off the second two terms and just takes off the first coefficient. And in general, notice that Q of 1, 0 is always a, that first coefficient, right? If I have a x squared plus bx plus c and I set y equal to 0, these things are gone. I set x equals to 1, I just get a. So maybe I'll do a little line like that. Can you see that? I have to slow down a little. Okay. All right. So, so it's positive definite. So what values are we seeing? Let's see if we can understand something about this. What values are we seeing of this quadratic form? Well, we saw the value, of course, 0, 0. So what numbers are we seeing? What numbers n? Okay, so we see n equals 7. What else can we find? Five. How'd you get 5? Q of what makes 5? 0, 1. Yep. So you can always see the value c. The value c will always be there for the same reason. You set x equal to 0, you set y equal to 1, you'll get the value c. Great. So we have 5 is represented and 7 is represented. So this isn't going to be one of those, the numbers that are 1 mod 4 or the numbers that are 3 mod 4, because we have both of those. Can we ever get an even number? Like, let's play. Take like, a good 10 minutes on your own and throw out some numbers. 0 is always represented. Yep. 0, we don't think about 0 because 0 is always represented. So aside, 0 is always Q of 0. Is always represented. The interesting thing is when 0 is represented by a indefinite form. Well, we'll talk about that. We'll come back to that. Right. So we have 5, 7, 1. Okay. So Sriya is telling us, look at Q of 1, 1. 1, 1 gets us 12 minus 11, which is 1. So 1 is represented. Great. 4. How'd you get 4? 2, 2. Very good. So here's another general principle. Now we know we get all the squares. Yukong, you were going to say something? Yes, we get squares. So we get all squares. Why? This is a general fact about quadratic forms. We talked about this already. If you replace x by kx and you replace y by ky, that's the same as the value at xy, except with an extra factor in front of k squared. Right. Does everybody see that? Yep. Exactly, Kevin. Exactly, Dependra. Okay, so this is another, maybe a better question. So better question. Not what are all the numbers that are represented, but what are all the numbers that are primitively represented? For exactly this reason. We want to get to the real heart of the problem and avoid all kinds of silly things. So a better question is, which n are primitively represented, i.e. n is equal to q of xy, and x and y have no factor in common. So we can get 4 by this imprimitive representation. Can we get 4 by a primitive representation? So is 4 represented primitively? So q of 2, 2 being 4 is an imprimitive representation. Imprimitive representation. Let's see, we're losing the form. I want to keep track of the form. There we go. Did anybody find what other? Just keep spitting out numbers. Try different values of x and y, and anytime you find one, spit it out. Seven. Yep, 7 we got. 7. Did you get 7 a different way than q of 1, 0? You got it a different way? What's another way? Okay. 2 and 3. Okay, so 7 is also q of 2 and 3. Let's see if I agree. This is a real calculation. 7 times 4 minus 11 times 2 times 3 plus 5 times 9. Oh boy. This is 66. I'm going to take 66 away from 45 plus 28. 45 plus 28, 60, 73. minus 66 is 7. That's interesting. Nobody else is finding representations? Okay, let's make a little table. Here's the value of q, here's x, here's y, and we'll plot q of xy. And x starts, let's do it like this. 0 is not interesting. 0 is not interesting because 0 comma, if x is 0, then I know then the value of y, if y is 1, then we get 5, and otherwise we get squares times 5. So any square times 5 is going to be there, right? For the same reason. The square of a represented number is going to be represented. So I don't want to start at 0, I'll start at 1. 1, 2, 3, 4, 5, 6. And y is 1, 2, 3, 4, 5, 6. Let's just see what we get. What are the values? So these will all be interesting. We don't want 2, 2 because 2, 2 is... Why don't we want 2, 2? Kevin, not primitive. 2, 4 is not primitive. 2, 6 is not primitive. And it's going to be symmetric, so we should only evaluate this is equal to q of yx. So that's not true. That is not true. Never mind. But the primitivity is symmetric. That's all I mean. Primitivity is symmetric. So 3, 3, the 3, 3 value we already know because it's going to be 9 times the 1, 1 value. So that's not interesting. 3 and 6 are not primitive. 3 and 6 are not primitive. 4 has a common GCD with itself and with 6. 4 and 6. 4 and 6, what is q of 4, 6? You guys should be able to answer immediately without any work. Q of 4, 6. Right away. Because we know what q of 2, 3 is. Yep, great job, Sriya. So it's 2 squared times the value of 2, 3. You guys see that? The value of 2, 3 we know is 7, so it's 28. So that's why I crossed out 4, 6. 4, 6 is not an interesting representation. It's not a primitive representation. We can get it from other information on the table. And 6, 4 by symmetry. 5, 5, 6, 6. So the diagonal is not interesting. But these are the remaining interesting values. So guys, why is 2 not primitive? 2, 2 is not primitive. Sheik, can you ask your question again? Which 2? Let's see, we no longer have the quadratic form visible. But I need the space. I'll rewrite the quadratic form down here. Q was 7x squared minus 11xy plus 5y squared. Why are even numbers not primitive? Pairs of even numbers, whenever you have a pair of even numbers, if x and y are both even, then there's no point in working out what q is for that pair. Divide both by 2, work out what the primitive value is, and then multiply by 2 squared. Does that make sense, Sheik? Why we don't care about those values? Okay. So I'm going to assign everybody a value. So 1, 1, actually 1, 1 we already know. 1, 1 was 1. What else did we work out? We worked out 0, 1, and 1, 0. Those are kind of over here. 0, 1 was 5 and 1, 0 was 7. So let's not forget them. They're still there, but there's no point in adding a 0 to the column because it'll be all x's. I'm just going to start assigning things to people. Or do you guys want to just choose one? Everybody choose one at random. And hopefully there's enough people. There's about 20 people here, and 36 minus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's close to, let's see if randomly everyone can provide one data point in here. So go ahead, pick a random point, and spit out the value of q. Tell me your point and tell me the value. Sarah's got one. One 5 is 77. 1 5. X is 1 and Y is 5. I have to make sure I get this right. 77. Okay, I'm trusting you guys on this. Kevin, 4 3. 4 3 is 25. That's interesting. That's interesting. Sriya, 2 1 is 11. 2 1 is 11. By the way, we worked out 1 2, didn't we? No, we didn't work out 1 2 yet. We didn't work out 1 2 yet. 8 7. Oh, 8 7. 8 7's not on my. Okay, 8 7's is over here. 3 4. 3 4 is 11. Interesting. Interesting. Yukong, 1 6 is 176. 1 6 is 176. Adriana, 6 5 is 47. 6 5 is 47. And Chang, 5 6. 5 6 is 95. Very interesting. What else? Let's fill up the table. Grab one that isn't there yet. Okay, 1 2 is 16. 1 2 is 16. 1 4 is 43. Thank you, Stephanie. 1 4 is 43. Yukong. 1 6 is 141. Oh, not 176? 1 6 is, oops, okay. It's very easy to make a mistake. I mean, we're doing, I don't know if this is quite second grade arithmetic, but 5 4 is 35. 5 4 is 35. We're almost there. Sheik's got one. Thank you, Kevin, for the 35. Five 1 is 125. 6 1 is 191. Thank you, Adriana. Sriya and Karen have some more coming in. One 3 is 19. Daniel's got one. 5 6 should be 25. 5 6 should be 25, not 95. All right. It's good. You guys are checking, hopefully, each other's work. 1 6 is 121. 1 6 is 121, not 141. Can two other people check 1 6? Oh, not 3 1, but 1 3 is 19. 1 3 is 19, not 3 1. 4 1 is 73. So 3 1 is not 19. 1 3 is 19. 4 1 is 73. Did we get clarification on this? Do I have to take out a calculator to work out what the value of 1 6 is? I'm gonna put or 121. I don't know which of these is right. Four 1 is 73. I got that. Come on, guys, we're almost done. There is a point to this. I'm not just wasting our time. 3 5 is 23. 3 5 is 23. 121 checks out. Okay, third time's the charm. 121 checks out. Can somebody get me 3 2, please? Okay, we're back. Okay, 3 2 is 17. 2 3, didn't we get 2 3 already? Yeah, 2 3 is 7. 2 3 is 7. I didn't put that in. 17 for 3 2. Yes, thank you. 4 5. 4 5 is 17. Thank you, Adriana. Stephanie, 2, 5 is 43. Karen. 3, 1 is 35. 3, 1 is 35. Thank you. What do we got left? Last two. 5, 2 and 5, 3. And we're done. Five, 2 is 85. Last one, 5, 3. $55. 55 is 5, 3. All right. I hope these numbers are right. We're going to find out how right they are. So you see the point. The point is, this is, fun and elementary and cumbersome, and we're seeing some numbers here. We're seeing 1. Well, we've seen 5 and 7. Those do count as primitive. The GCD of 0 and 1 is 1. So 5 and 7 are primitive values. So which values have we seen? Dipendra, you're saying something? Is it a coincidence that the row for 5 is plus or minus 1 mod 4? The row for 5 is all 5s? Oh, this row of 5? The row of 5. The row of 5. Well, yeah, something, by the way, is bothering me a little bit. Did anybody check 1, 2? One, 2 is 5. Is that right? Daniel? That's what you're saying? 1, 2 should be 5, not 16? 1, 2. All right, let's just do it. 1, 2, Q of 1. I'm going to check one of your values. That one's suspicious to me. I'll tell you why. Okay, 5. Good. Okay, good. So 7 minus 11 times 7 times 2 plus 100. Is that right? Wait. 1, 2. That's 7. 11 times 1 times 2. That's better. That's better. That's okay, Sarah, but now I can't get it right. 7 times 1 minus 11 times 1 times 2 plus 5 times 2 squared. 5 times 4 is 20. Not 20 times 5. Okay. 27 minus 22 is 5. Okay, good. You see how easy it is to get this wrong. Okay, so this is 5. Now the reason that was the one that was that I had suspicions about is look at all the numbers. All the numbers are... It's okay, Sarah. All the numbers are... Sriya? Odd. Yes. All the numbers are odd. So let me make this an exercise. Primitively, imprimitively, we can take all square values like 4 and so on. Q only takes odd values primitively. Let's see, this is kind of saying the wrong thing. This is saying that if it takes an odd value, then it takes it primitively. But of course it takes 9 because it takes 1. It takes 1, so it takes 9. And that's not a primitive value, and I don't see 9 primitively. Primitive values of Q are odd. Let's do it the other way around. Primitive values of Q are all odd. And that's an easy exercise. How would you prove this? Wait, but doesn't that depend on what... I mean, for this Q. For this particular Q. That's not true in general. Right? X squared plus y squared takes the value 2 primitively when x and y are both 1. So you're absolutely right, Kevin. Of this Q are all odd. How would you prove this? This is easy. You want to take 5 minutes, take 2 minutes, and see if you can see how to do this. Why are all the values in the table plus or 1 mod 4? Well, once you're odd, all odd numbers are either 1 mod 4 or 3 mod 4. Oh, you can't hear? Can you hear me now? You guys, can you hear me? Sort of. Uh-oh. Karen, Stephanie? Oh, it was spotty. Okay, but now it's okay. All right. Sorry about that. Okay, that's better. So how would you prove that the values of Q are all odd? In fact, all you have to do is point to something. There's a very easy thing to do now that we have this whole table. X and Y cannot both be even, right? If X and Y were both even, then you would certainly get even values. But there's something very simple. X and Y are coprime, right? So they can't both be even. That's what I mean by primitive values. The coefficients are all odd, yes. And this will be true whenever the coefficients are all odd. So what that the coefficients are all odd? Why does that force the way odds and evens multiply and add? Yes. You're all saying the same thing and the right thing. If you just look in this first corner, here's the solution to the exercise. The solution to the exercise is that modular arithmetic is arithmetic. In other words, if I want to know what the values of Q are, mod 2, just reduce Q mod 2. But that means the only x's and y's to check are the ones mod 2. And 2 is the thrown out value, because we don't want imprimitive values. And then I have 1, 1, 1. So Q always takes the value 1 mod 2. You see that? Ooh, yes. Nice. Now you can sort of look and see what happens. All right, how about mod 3? Well, all I have to do is, if I want to know what the values it takes mod 3 are, okay, so exercise 2. Exercise 2. Let's see if we can vary now with this hint. What values does Q represent primitively mod 3? Does it represent 0? Does it represent 1? Does it represent 2? Those are the 3 values mod 3 that Q could represent. So what would you do? It should involve 0 computation. Well, a little bit of computation. Very little, though. Sriya? Yeah, exactly. Repeat exactly what we said about the values of 2. So where in the table should I look? Where in the table that we've already worked out should I look? Surya, do you want to say more about what you're suggesting? Exactly. Reduce all the values. So in order to understand the values mod 3, we just have to look in this corner. As x ranges from 1 through 3 and y ranges from 1 through 3, all the values that we see here when we reduce mod 3 will be exactly what happens to q mod 3. Right? The block will completely repeat wherever we move it around mod 3. Does that make sense? So do we see the value 1? So q mod 3, imprimitively, we can take the value 3, 3, and we know that that's a multiple of 9. That's cheating. Q mod 3 is, so this is the answer, I see 1. 11 is 2. Yes. Mod 4, exactly. Mod 4 is the same logic, but Dipendra, once we know that it's odd, that it's only odd, the values mod 4, all the values mod 4 are possible. The only odd values mod 4 are plus or minus 1. Right. So 11 is 2. Do we see the value 3? Are any of these 1, 2, 3, 4, 5, 6, 7 numbers, are any of these multiples of 3? Okay. Either I lost you guys or everyone is following and it's trivial and no one wants to say anything. Sheik, did I lose you or are you following along? Okay, thank you, Sheik. Let's go back a little bit. So I'm trying to figure out what numbers Q represents mod 3. Okay? Sheik, do you want to unmute yourself so that we can chat, or you're... I see the headphones. That means you didn't log in to speak. I think in general, is there any reason to do that, or is there any, or I think in the future, if you guys could log in and just mute yourselves, so that if you do want to speak, you should always be able to speak. So Sheik, do you? I guess there's no way to switch without leaving and coming back in. Is that right? Do you want to do that? Take a second and log out and log back in, and okay, so that then we can talk. Yeah, I encourage you guys to come in and be able to talk and just mute yourselves for the purposes of the computer not getting the reverb. Hey. So what values, say that again?
What values are we looking for Q mod 3?
So in order to understand what Q does mod 3, I have to check what it does mod 3 for all possible values of x and y mod 3.
Okay.
But the possible values of x and y mod 3 are 1, 2, or 0, or 3 for x, and the same thing for y. So I've already worked out what the values are in the integers. So it's enough to look at the values in the integers and reduce these values mod 3. And that gives me the complete table of the values that Q can take mod 3.
So we reduce them into what?
So I'm reducing all of these values. I'm reducing 1, 11, 35, and 7, and 17, and 5, and 19. I'm reducing those mod 3.
Oh, okay.
Does that make sense?
Yeah.
So I'm seeing 1 and 2, but I'm not seeing 0. None of these numbers are multiples of 3.
Yeah.
So not 0. So already, without doing more work, no number that's a multiple of 3 will be primitively represented here.
Okay.
And also no even number will be primitively represented.
Sure.
Does that make sense?
So no multiples of 3 would be represented and no even numbers would be represented in that table, right?
Yes. No multiples of 3 will be primitively represented. And for the same reason, from the previous exercise, this was exercise 1, no multiples of 2.
Actually, I want to ask you a very silly question.
Please.
And it's that, what is primitive? When you say what's primitive, it means that
Yes. So a number is primitively represented if it's represented by x and y that are co-prime.
Oh, right, okay.
So what I'm trying to avoid is this situation where if x and y have a factor in common, then the square of that factor can just pull out.
Oh, okay.
Okay, does that make sense? Thank you for clarifying that. I'm sure there are lots of other people that are confused about this point. So we switched from all values to only primitive values exactly because of the homogeneity of the quadratic form. It's a homogeneous polynomial of degree 2, so if x and y have a factor in common, we can pull out the square of that factor, and that'll give the value of the form.
Okay.
Okay?
Makes sense.
Great.
Thank you.
Let me just catch up to your questions. Stephanie, exercise 2? Exercise 2 just tells us that the values cannot be a multiple of 3. Exactly. Primitively represented values will not be multiples of 3. Was there a proof that all the values are odd, or did we conclude that by observation? It's again exercise 1. The primitive values are all odd, which we proved by looking at the values mod 2 in the top 2 by 2 corner. So we never saw 2 represented. We never saw none of these numbers are 0 mod 2. So the form will never be 0 mod 2 primitively. Now Dipendro's question. Kevin has a great question. We're going to come back to your question in a second, Kevin. Dipendro, slightly random. In mod 4, q becomes that thing. So for xy in second or fourth quadrant, we will have q is x squared minus xy plus y squared. So I was wondering if there's a connection between the thing we did with numbers represented by Eisenstein. So, yes and no. Yeah, I'm not ready to talk about genus yet, but very soon we'll talk about genus. And 2 quadratic forms are in the same genus if they represent all the same numbers, mod p for every p. But that doesn't always. I'm really getting ahead of myself now. But that doesn't always tell us what numbers it represents in the integers globally. So, Dipendra, you asked a great question. I have to defer it for a little bit. So it tells us what numbers. It tells us mod 4 that the Eisenstein quadratic form and this random quadratic form have the same values. But we already knew that just by looking mod 4 at what values they take. So that doesn't help us that much, but that's a really interesting observation. Kevin, you also have a very interesting observation. What if A, B, and C are themselves not primitive? So that's another use of the term primitive. The term primitive gets also overloaded in this business. So let's just say that for a second. There's a quadratic form being primitive, and then there's a number being primitively represented by a quadratic form. So let's make that distinction. So 2 definitions. A quadratic form Q given by ABC is primitive if the GCD of A and B and C is 1. So an imprimitive form, e.g., an imprimitive form Q would be 2x squared plus 4xy minus 6y squared. That's just silly. If you have that form, you may as well look at twice all the values of the primitive form, x squared plus 2xy minus 3y squared. Right, it doesn't have to be pairwise primitive. So this form is imprimitive. So the values, so it's not interesting to check what happens to its values. Check the values of this one and double it, and that tells you everything about the values. So values taken by Q are simply twice values of this primitive guy. Okay? Here's an example. Here's another example. Is 2x squared plus 3xy minus 6y squared primitive? Depender asked about pairwise primitive. So no, oh, sorry. Hang on. I got this wrong. 2 times 3 is 6. 2 times 5 is 10. 2 times 3 is 6. 2 times 5 is 10. And 3 times 5 is 15. Is this form primitive? Here's a question. Is this form primitive? Every pair has a factor in common. 6 and 10 have 2 in common. 10 and 5 have 5 in common. 10 and 15 have 5 in common. 6 and 15 have 3 in common. Yes, Kevin is correct. This is primitive because there's not some other form whose values we can use to work out the values of this form. Okay? So primitive form does not mean pairwise primitive coefficients. Okay? So this form is primitive. There's not some other form that we could use to work out its values. We have to deal with it. All right? So there's what it means for a quadratic form to be primitive, and then what it means for an integer to be primitively represented, or a primitive representation. A primitive, let's just write this again, we had it a second ago, but it's worth repeating, representation of n being q of xy is one with x and y being coprime. Okay, so there's primitive representation as opposed to primitive form, primitive or imprimitive form. Does that make sense? Is the distinction between those two clear? All right. Let me put my table back for a second. As long as we looked at the values mod 3 and mod 2, what about mod 5? Exercise 3. What values does Q take mod 5? And can you raise your hand in the, the chat thing? Not the chat, you know what I mean. In your profile picture. Can you raise your hand if you know exactly what you're supposed to do now, given this table, to work out what the values mod 5 are? And can you give me, I don't mean raise your hand. Give me a thumbs up if you know exactly what to do. Give me a thumbs down if you're at all unsure about what you have to do next. Okay, Stephanie, thank you very much. I'm sure there are lots of other people. Can I pick on you? Can you unmute yourself? Okay, so what values will Q take mod 5? How do we figure this out? Well, that's why I'm picking on you, because you don't know the answer yet. So now we get to actually learn something.
Going off the first, do we just draw the box around 5? Yeah, and we just find the values mod 5.
So it turns out you do know the answer.
Wait, that was it?
That's it.
Oh.
That's how simple this is. Do you see why? It's because modular arithmetic is arithmetic. Whatever you did over the whole numbers, you can first reduce mod 5, or you can do the arithmetic first and then reduce mod 5, and you'll get the same values. So all we have to do is reduce this box, this 5 by 5 box, which all you guys generously worked out, hopefully correctly. I don't know who's checked these things, but let's see what values what values does Q take primitively. We only worked out the primitive values, primitively mod 5. So Q mod 5 is, what do we see? I can't show both things at once. I can if I fold. There we go. So Stephanie, can I continue picking on you? Tell me, just shout out some values that you see in this first box.
So for the first row,
Yep.
it's 1 1 0 3 0.
Okay. Second row.
0 2 0.
Third row.
4.
And we're done.
2. Oh,
Because we see everybody.
so mod 5 doesn't tell us much then.
Doesn't tell us anything. We've learned nothing from mod 5, and I think if you continue, you'll see that a lot of the values... well, let's think about this heuristically. In every box, in a K by or P by P box, so let's look at a heuristic. Okay, so heuristic in a P by P box, we have about, well, right, we don't have all the values, we don't have exactly P squared values, but we have roughly, because we're not looking at the imprimitive values, we have roughly, let's say roughly, P squared values to investigate, to check. And they're all numbers mod P. And they are all numbers mod P. So the larger P is, the greater the chance that you fill out everybody. Because you have so many values, you have P squared values that are all getting collapsed onto numbers from 0 to P. P minus 1. So for larger and larger P, so for larger and larger P, the odds are getting better and better that you'll find everything. Odds are better and better that you'll find all values. Now that's just a very rough heuristic, and we don't know if that's true. All right, we're still just experimenting. We're trying to figure out what's going on. Let me introduce an idea which was extremely crucial in Gauss's observations. What we did here is we didn't change Q, we changed the values of X and Y. What is the dual idea to that idea? We kept Q the same Q, and we changed the values of X and Y. This was a crucial moment in people's understanding. Sarah? Yes, exactly. Exactly. So here's a crazy idea. I'm going to leave this table here still. I'm going to try. Let's see if I can figure out how to do this. So here's a crazy idea. Crazy and important idea. Duality in mathematics is absolutely fundamental concept and one that appears over and over again. So dual idea. Instead of changing x and y, instead of keeping q and changing x and y, fix x and y, and change q. What in the world do I mean by this? Okay? What in the world do I mean by this? Let's look all the way back. We have our q. Let's call this q0. q0 was 7x squared minus 11xy plus 5y squared. And we immediately knew that its value at 1, 0 was 7 because that's equal to a. And when you plug in 1, 0 for any q, it's just the x squared term. That's the only thing that survives. Right. Exactly, Kevin. We're about to change the coefficients. So I want to know what is the form if I, instead of changing xy from 1, 0 to 1, 1, I want to think about changing q0 to something else and evaluating it at 1, 0. Evaluated at 1, 0. So it's actually harder to understand what's going on in an explicit example and easier to understand what's going on, I think, abstractly. So let's just see what I mean by that. Right. So remember that we had this discussion about quadratic forms being essentially the same. Have we talked about this? When two forms are equivalent? No, of course not. That would be begging the question. So two forms. Let me give you a form. Let me make up a form right now. Well, let me show you what I'm doing. So here's the thoughts. Idea. X squared plus y squared is one quadratic form. So in this quadratic form, replace x by x plus y. So that gives me a new quadratic form, x plus y squared, which of course simplifies to x squared plus 2xy plus a y squared and another y squared, so I get 2y squared. Does that make sense? So the values, so let's call this form, let's see, I want to leave this as q0. Let's make this q1, and let's make this q2. So what values does q2 represent? My claim is that q2 primitively represents exactly the same values as q1. Why is that? So give me a representation of some number as a sum of two squares. Q1 of 1, 2. Three, 4. Perfect. 3, 4. Q1 of 3, 4. 3 squared is 9. 4 squared is 16. This is our 3, 4, 5 Pythagorean triple is 25. I claim 25 is also represented by Q2. find x and y such that Q2 of xy is 25. So I want x and y, so that if you take x squared plus 2xy plus 2y squared, you get 25. Daniel. -1, 4. Yes. Did you guess, or how did you do it? Yes. Excellent. Excellent. You didn't have to guess. So solution. Beautiful. The solution is Q2 of -1 comma 4 works. Let's check that it does work. Q2 of -1 comma 4, that is -1 squared is 1 minus 2, because there's a -1 times 4 plus 2 times 4 squared. Okay, I'm just evaluating what Q2 is. So 4 squared is 16 times 2 is 32 minus 8. 32 minus 8 is 24. And plus 1 is 25. Equals 25. Now, what Daniel did is exactly the right thing. Remember, Q2 of xy is, because of how we created it, Q2 of x comma y, this is Q2 of x comma y, is Q1 of x plus y comma y. Does everybody see that? If I stick in x plus y in place of x, then Q1 of x plus y gets us x plus y squared plus y squared, which is how we define Q2 of x and y. So Q2 of x plus y is equal to Q1 of x plus y, and so what Daniel solved the system of equations x plus y is equal to 3 and y equals 4. Well, that means y is equal to 4, and if y is 4, then x is -1. Does everybody see that? So the point is that Q1 and Q2 differ by an invertible linear change of variables. Differ by an invertible. You see, all right, I'll come back to that in a second. By integer invertible linear change of variables. Okay, does that make sense? Should I give you another example of this? Let's do another example. Let's do another example. Another example. Find x and y such that Q2 of xy is equal to 2, 3, 2 squared is 4, 3 squared is 9, 13. And 13 is 1 mod 4, so I know that there's a representation. Okay, let's see if you understood this trick. Let's see if you understood Daniel's trick. First of all, how is 13 a sum of two squares? Yukong's got it? Sriya's got it? A bunch of people are writing in. Yes, it's a linear transformation, exactly. Sriya, were you going to say something? It's okay if it's wrong. It doesn't have to be right. Very good, Dipendra. Sheik, you got something? Yes. So Sheik is reminding us that 13 is 4 plus 3, 4 plus 9, which is Q1 of 2, 3. And the difference between Q1 and Q, so Q2 of xy, again, is Q1 of x plus y. And so I want x plus y to be 2 and y to be 3. And so I should take, xy should be, y should be 3, and 3 plus what makes 2? Negative 1. Oh, so Q2 x, yes, exactly, Shriya. Exactly. So Q2 of negative 1, 3 is indeed 13. And I'll let you verify that that's correct from first principles, since now I don't even see where Q2 is. Q2 is all the way up here. Sorry. Okay, does that make sense? Should a change of variables be linear to be useful? If it's not linear, then what you will get, if I replace Q1 by Q1 of x plus y squared y, then this will no longer be a quadratic polynomial in y. The degree will be will be a higher degree thing. Yukong, I guess two quadratic form can represent the same integers when the translation is invertible in Z. Excellent. Excellent. So here's a definition. Now, just one more thing from linear algebra. Do you guys know about general linear groups? Have you seen general linear groups? Yes. Okay, good. So recall GL 2 by 2 integer matrices. So these are matrices A, B, C, D, with A, B, C, D integers, A, B, C, and D integers. And in order to be invertible, what do I need to know about this linear transformation? Determinant. The determinant, what's the determinant of the matrix A, B, C, D? So determinant, which is AD minus BC, AD minus BC. So in the real numbers, what's important is for the determinant to be not 0. So maybe first I should say GL2R. GL2R is the determinant isn't 0. But if I want it to be invertible and invertible by another integer matrix, GL2Z is, so this is real entries, is, I'm running a little out of time, so let me say this quickly. So this is now with A, B, C, D in the integers, and then in order to be invertible, the determinant has to be an invertible integer. And the units in the integers are plus or minus 1. Okay? So here's your exercise. Exercise. If Q is equal to ABC, what's SL? SL is, okay, and SL2 is the matrices, let's call them gamma, in GL2 with determinant equal to +1. So SL is special linear. SL has determinant +1. GL has just any invertible determinant, but to be invertible in the integers, it has to be plus or minus 1. Okay, so here's the exercise. If Q is quadratic form ABC and gamma is ABCD in GL2Z, so this is supposed to be a linear transformation. It replaces, so how does ABCD act on a pair XY? It replaces X by AX plus BY, and it replaces Y by CX plus DY. So the question is, what is, let's call this Q, okay, if this is Q1, what's Q2 of XY? Which is Q1 composed with this matrix, Q1 composed with gamma, which is Q1 of AX plus BY, CX plus DY. So if Q2 is written as A2, B2, C2, really do this exercise. This is an important exercise. Work out what A2, B2, and C2 are in terms of A, B, C, and A, B, C, D. Okay, this is a fundamental exercise. If you can just do this computation, in other words, stick this thing in for x squared, stick this in for y squared, and stick these two in for x, and multiply everything out and collect the terms of x squared, and collect the terms of xy, and collect the y squared terms. We will next time reinterpret this table as keeping x and y the same, but just changing the quadratic forms, moving around quadratic forms instead of moving around pairs of integers. And that will open up a whole new world of things to study.